Hi there, I'm Sawyer, and welcome to Real Numbers, a show that solves real-world problems using mathematical techniques. Our current sequence of probability puzzles will be capped off in today's and next week's episodes by a discussion of Bayes' theorem, one of the first foundational results of probability theory. Let's present the motivating problem of the week. Evelyn administers the written tests at her local DMV. Before each applicant takes the test, she asks them if they studied for it. She's found that 60% of applicants have studied, and while the overall pass rate for the test is 75%, for the subset of applicants that haven't studied, only half pass. She just had an applicant take the test and pass, and she forgot to ask them if they had studied. What is the probability that they studied? In this problem, we have a known conditional probability, the probability that someone passes the written test given that they haven't studied for it. This would be written, the probability of pass given did not study. And it tells us the ratio of passing within the subset of applicants that have not studied. Now what we were asking for is the probability that a person who is known to have passed studied for the test. This would be written, the probability of studied given pass. Note that we have switched the event of interest, that is the event we are asking about the probability of, with the condition, that is the event we know happened. For any two events A and B, the theorem that allows us to relate the probability of A given B to the probability of B given A is known as Bayes' theorem. A common application of this theorem at Jane Street comes in the form of Bayesian inference, which determines the relative accuracy of a set of models given empirical data that the models are trying to represent. Bayes' theorem states that the probability of A given B equals the probability of B given A times the probability of A over the probability of B. Proving this theorem is actually very straightforward, using the equation we learned about conditional probability. Remember that for any two events A and B, we have the probability of A and B equals the probability of A times the probability of B given A. But notice that the event A and B is equivalent to the event B and A. The mathematical way to say this is that the logical operator AND is commutative, but there is some common sense to it. If the muffin was warm and delicious, then it was delicious and warm. Now, using the conditional probability formula again, the probability of A and B equals the probability of B and A equals the probability of B times the probability of A given B. And combining these together, we get the probability of B times the probability of A given B equals the probability of A times the probability of B given A. Dividing both sides by the probability of B gives Bayes' theorem. The probability of A given B equals the probability of B given A times the probability of A over the probability of B. Try to employ this theorem to help compute the problem of the week. Now let's solve last week's challenge about the card game of War. There is a link to that episode in the description of this video if you need a refresher. Clara and Damien were about to make the first move in their game of War, where Clara had the 13 clubs shuffled up, and Damien had the 13 diamonds shuffled up. We were wondering about the probability that Damien loses his ace of diamonds once the dust had settled after this first move. The only way for a player to lose an ace in War is for a war to occur. That is, the top cards of Clara and Damien's decks have to be the same rank. It's easy to see this, since aces always win battles that aren't wars. So for Damien to lose his ace, we need the top card of his deck to match the top card of Clara's deck. Whatever card Damien flips, Clara's card has to be exactly one of 13 cards in her deck that has an equal chance of occurring. So the probability of a war is 1 over 13. Now, there are three disjoint ways that Clara can win Damien's ace. Either Clara and Damien tie with aces, and Clara wins the subsequent war. Clara and Damien tie with non-aces. Damien's ace is in the next 3 cards, and then Clara wins the war, either outright or by coin flip. Or Clara and Damien tie with non-aces, and then after the next 3 cards, Clara and Damien tie with aces, and Clara wins the subsequent coin flip. We will compute these probabilities individually and then add them, since they are disjoint. We can see that these cases are disjoint because each one has Damien's single ace showing up in different places in his deck. In the first scenario, we have the probability of Clara and Damien tie with aces, and Clara wins the subsequent war, equals the probability of Clara and Damien tying with aces, times the probability Clara wins the subsequent war, given that Clara and Damien tied with aces. Because the remainder of Clara and Damien's decks are equal after the aces are set aside, by symmetry, Clara and Damien each have a 1/2 chance of winning the subsequent war. So this probability is 1/13 times 1/13 times 1/2, or 1 over 338. In the second scenario, we have the probability of Clara and Damien tying with non-aces, and Damien's ace is in the next 3 cards, and Damien loses the war. That's 12/13 times 1/13 times 3/12 times the probability Clara wins the war given they tied and Damien's ace was in the 3 extra cards. The easiest way to compute this last factor is to split it up into the case where Clara draws her ace or doesn't. When she draws her ace, she always wins against whatever Damien draws. Given she didn't draw her ace, her deck is identical to Damien's, so she has a 1/2 chance of winning the war. So this probability simplifies to 1 over 104. In the final scenario, we have the probability that Clara and Damien tie with non-aces, and Clara and Damien then tie with aces in the war, and Clara wins the coin flip, which is this large product that simplifies to 1 over 4056. So the total probability that Clara wins Damien's ace on the first turn of the game of war is 1 over 338 plus 1 over 104 plus 1 over 4056, which is 1 over 78. Wow, that simplifies a lot! Often when a problem's answer simplifies significantly, there's a more direct way to compute the answer. Maybe you can find an easier way to compute this. Okay, let's recap this episode's problem of the week. Evelyn knows the following. 60% of written test applicants have studied. 75% of written test applicants passed the test. And given that an applicant didn't study, he or she has a 50% chance of passing. What is the probability that an applicant who passed the test studied for it? Submit your answer on this page showing your work. Also, if you come up with a problem of your own, or just an observation about this or last week's problem, please share it using the button on this page. See you next week for a solution to this problem and another Bayesian math challenge.